Hello and welcome to the second video in my series on the IBM 8514/A video standard from 1987. There's a link above if you want to check out the first video where I cover a little of the history of the standard and some of the PCI cards that supported it. But the summary is the 8514/A is a video standard introduced by IBM alongside their VGA standard for their PS2 line of computers in 1987. It came in the form of an add-on adapter card which added a graphics coprocessor to the system, with a Blitter no less, that enabled you to draw graphics primitives in hardware. Now, it was a professional standard and so it came with a high price tag, over $3,000 for the add-on adapter card, the additional VRAM you needed if you wanted 256 colors, and the IBM 8514 monitor, which supported the two graphics modes of the standard, 640/480 and 1024/768. Now, a little later, other graphics manufacturers produced clones of the 8514/A standard, and in today's video, I'm very pleased to present one such card. This is the ATI Graphics Ultra. It's a fairly rare and expensive card, and at first sight you'd be forgiven for thinking it's an ordinary VGA card. And you'd actually be half right. There are two chips in the middle here. One is an ordinary VGA core, and the other one is the ATI Mark 8 chip, which provides the 8514/A coprocessor functionality. Now, the exciting thing about this card is that it's a 16-bit ISA card, so it should, in theory, plug into a 286. And so one of the things we're going to find out in today's video is whether it will actually work on that machine. Now, the other thing that I've discovered since the previous video, which is also very exciting, is some of the original files for programming the IBM adapter. Now, if you Google tutorial for the IBM 8514/A, you'll find reference to an IBM tutorial which seems to be long gone. If you know where I can find a copy of that, let me know in the comments below, although remember that YouTube will remove links, so you'll have to describe where you found it. But that tutorial refers to various files on a driver disk that I have managed to locate. I found it in the archive of Jim Leonard, aka Trickster, who was a PC archivist, and they're on an IBM driver disk that came with one of the PS2 machines in question. So I'm very excited to figure out whether or not those files will actually allow me to program this ATI card, and I have reason to believe that they will. And I hope you're interested in this as well, because we're going to find out this together in today's video. Here's a close-up of the board, and the big chip in the middle, which is a little bit hard to read in real life as well as on the photo, is the ATI 28800-6. This is the VGA core, and you'll find this chip on a lot of other ATI video cards as well. And right next to it, at the edge of the card, is the other big chip, the ATI 38800-1, and that's the coprocessor that does the 8514/A functionality. And over on the end of the board, you'll find a bunch of chips that look like VRAM, and that's exactly what they are. So these are TMS 44C251-10s, and they're each 256K by 4 bits. So with 8 of those, that means we have a whole megabyte of memory. But right next to them, you can see another 4 chips soldered to the board. These are TMS 44C256-80s, and with 4 of those, that gives us another half megabyte. They're also 256K by 4-bit chips. So I guess we have 1.5 megabytes in total, which should mean that we get the 1024/768 256 color mode. Now, if we have a look over at the BIOS, we can see it says Graphics UV, and I assume this stands for Graphics Ultra. I'm not sure what the V stands for. There was actually a Graphics Vantage as well, and the difference was just in the memory that was used. So the chip next to that is the RAM DAC, and this is a KDA 0476PL-80, and this is 256 18-bit words, obviously for the 18-bit color of VGA. And then you have the two crystals. It's a little bit hard to read one of these as well, but one's 33 megahertz and the other one is actually 45. Now, I should explain why I think it's going to be possible to program this card. These are the files that I found on that IBM driver disk, And if we look in the only assembly file here, call afi.asm, it just has two functions. So the first function at the bottom of the file here is for getting the adapter interface address. And all it's using is a call to interrupt 21H and interrupt 7FH. So these are just interrupts that should be available on my card. And the other function is for actually calling the adapter interface, so calling one of the functions that it provides. And these are just done by function number. So it's actually a really straightforward interface that should work with any card that supports the 8514A interface. So the only other thing here is some C files. There's IBM AFI.h, and this is actually the interface for a C program. And basically it just lists a whole load of functions that you can call, and it does them by calling an adapter function by number. So for example, hopen is just function number 8, and then there's some block of data that you have to pass to the function. Well, it turns out that you can also figure out what the data should be as well, because there's another file called afidata.h, and as far as I can tell, all this is a bunch of structs for C, so these are just data records if you like, that contain the data for each of the different functions that the interface provides. So for example, if you want to call the hscol function, then you have to pass some data which consists of a length and an index. So this is actually really straightforward to use if you know anything about C programming. Now there's two other things that we're going to need, and the first of those is a description of what the adapter functions actually do. You can see that all the names are abbreviated, and it's a little bit hard to figure out just from the name what it might actually be for. But this document in a book called PC Graphics Handbook actually lists all the functions, both by function number and by name, and it tells you what they actually do. For example, hline is just for drawing a line, and so on. And this goes on for a couple of pages here, and actually all of these will work on XGA as well. It turns out this book also gives some additional functions which only work on XGA, so they won't be relevant to us today. And the other thing that would be nice to have is an example of how to use all this, and it turns out that on that driver disk there's htidemo.c, which is a C program which I can compile, and it's actually the source code for the HDI demo that we showed in the previous video. So if I open this up here, what we'll find inside is a complete program that we can use as a template for actually calling adapter functions. Inside this program it has this draw quad function, which is actually something that they define inside this particular file. So there's the draw quad function down here. It just puts some data into some coordinates, and then it sets a color, and then it starts a fill area and just draws all of the points of the quadrilateral, and then ends the fill area, which should actually fill in a quadrilateral. So it's a really good example of how to use the fill function of the 8514/A. So I think we have enough here to actually get started and to try and write something for this card. Now the good news is the card seems to work in this 286, and if I run the HDI load program, which is the driver for the 8514/A, then I should be able to run HDI demo.exe, which is a compiled version of the program that we want to get running. So at least that should work. And yeah, it does actually seem to be working. At least it's drawing quadrilaterals on the screen. You can see it is running off the top and the bottom of the screen. That's probably because it's in a mode that this monitor doesn't actually support. But that's no problem. We can probably work with the 640/480 resolution and everything should be fine. Now I have actually noticed a minor problem with this card. Some of the characters are being repeated on the following line. For example, if you look at the first Borland International at the bottom of the screen, the B and the L are repeated in the following blank line. And if you look at the README in the directory listing, you can see that the S and the L have dropped down from the install immediately above. And I guess this is something to do with the scroll function, but I don't notice it in my text editor even when I scroll the screen there. So I'm not actually sure what's causing this, but it is just a minor inconvenience that I can ignore. It's not affecting the functionality of the machine itself. Well, I did manage to get it to compile with Ball and Turbo C instead of the original IBM C compiler that we're using, and I had to rebuild the assembly file as well because the object file format they use is a bit different. So you can see that it's working, but there were a few issues that I had to sort out related to the differences between the compilers. For example, there's a 400 byte block of memory allocated in a weird way with the IBM compiler, and I had to use the far-malloc function of Turbo C to do that correctly. And a really big issue was the palette cycling. They were doing that by copying blocks of memory around inside the palette table. But they were using memcopy for this, and that's fine so long as the blocks of memory don't overlap. And unfortunately they do, and it's undefined behavior. So I had to change that to memmove, and that finally fixed the problem. As you can see, there's no text on the screen, and that's because the Mark 8 chip from ATI doesn't actually support the fonts of the 8514/A. The Mark 32 chip did, and I sped it up a little bit. It's 100 milliseconds between each iteration of the palette cycling now, and it just makes it look a little bit more lively. And obviously I've changed the resolution to 640/480 using the set mode function of the card, and this is a little bit easier on my monitor and also a little easier to film as well. Well, the first thing that I've done is code up 10,000 random rectangles on the screen. And remember, we did this with the Mark 32 card on a 486, and we got 10,000 rectangles in 10 seconds. So basically 1,000 a second. So let's see how long it takes here. And it looks pretty quick for 286. Oh, that's 4 seconds. That is insanely fast. So that's actually way faster than we had on the 486. Well, remember that when we were doing the timings for the 486, we were using the Ball and Turbo C VGA interface for the IBM 8514, and I'm betting that just doesn't do anything special. And now that we're using the proper IBM code, we're actually getting the proper rectangle drawing capabilities of the card, which are really insanely fast. So I think we can do something really quite amazing with this. Before moving on, I decided to check if the card can fill random polygons as fast as the random rectangles that we already saw. So I wrote some code for drawing random quadrilaterals and filling them, and this time the edges won't be parallel with the sides of the screen, they'll be at random angles, and I'd expect shapes like that to be slower to fill, but the result is really surprising. Let me show you. As you can see, it's really slow. I clocked this at 60 quadrilaterals a second, about 1 a frame, which is way too slow. And doing some reading, it seems the IBM adapter interface might be responsible. This is given by that HGI load.exe program that we found on the IBM driver disk. It translates adapter function interface calls that we've been using down to register level code for the hardware itself. The reason that works with our ATI card is that it implements the 8514/A interface at the register level. It even adds some additional registers that are ATI specific, by the way, including ones for speeding up polygon fill, but none of that should be necessary since IBM already has hardware for every step of a polygon fill. So I have no idea how it can be so slow. The way you normally fill a polygon with the 8514/A is to first draw an outline in an off-screen buffer. It doesn't have to be system RAM, it can just be a piece of video RAM that's not currently displayed. And there's actually a hardware implementation of the Bresenham line drawing algorithm specifically for this. And you can set it up so that it draws just 1 pixel per scan line when drawing the lines. And this means that for each scan line of your polygon, you'll have 1 pixel filled in on the very left of your polygon and 1 on the very right. So all you need to do is fill in all the pixels in between for each scan line. And it turns out that there's hardware for that as well in the 8514/A, the polygon fill routine, if you like. And then the only step that remains is to copy that filled polygon from the off-screen buffer onto the screen. Of course, you don't want to overwrite any of the pixels that are outside the polygon, otherwise you'll mess up your background. But it turns out that the Blitter, which is specifically for this purpose in the 8514/A, can actually do this. So I have no idea why it's so slow, but it looks like the only way we're going to get anything faster is to program the ATI card at the register level. This would be a lot of work, except that it turns out you can combine adapter interface level programming with register level interface programming. And this is done by doing all the boring stuff at the adapter interface level and all the stuff that needs to be fast, like Polygon fill, at the register level. And so I guess this is what I'm going to have to try next. Well, the first thing I did is use the 1 pixel per scanline option to draw lines. And I made a little draw triangle routine out of this. So it's just going to draw random triangles on the screen. So let's just do them one at a time at first and see what they look like. And you'll notice that some of the lines look dotted, and that's because there's just 1 pixel per scan line. So if the line is really horizontal, then there's a long distance between each pixel. So we'll just draw a few of these just so you get an idea of what that looks like. And then it's going to draw 10,000 of these as fast as it possibly can. And I make that about 2 or 3 seconds, so that's obviously not a bottleneck in doing polygon fill on this card. So let's push on and actually fill these triangles in. Well, this is what I came up with, and this would normally be in an off-screen buffer. I'm just showing it here so you can see what's going on. We draw the triangle in outline and then use the polygon fill, and there are a couple of things I had to look out for here. First of all the lines have to be drawn in the same direction, for example from the top of the screen towards the bottom. And secondly, at the vertices of the triangle, the edges are going to intersect in a single point. And this is problematic for the fill routine. It needs a point on the left side of the triangle and one on the right side of the triangle for each scan line of the triangle. And at those vertex points, there's just going to be a single point on the scan line. So in order to fix this, we actually XOR the lines onto the screen. And this way, any points that coincide will cancel each other out due to the XOR, and that fixes the fill. And the other thing we need to do, of course, is to blank this triangle, after blitting it into the visible portion of the screen, of course, so that it doesn't interfere with the next triangle that's drawn in the off-screen buffer. So to do that, we just draw a black rectangle around it and fill it using the very fast rectangular fill that the card provides. That's very quick. And then we're ready to draw the next triangle, fill it in and blank it and so on. So we're going to do about 10,000 of these just to see how long it's taking at this point without the blit. And the answer is it takes 40 seconds in total, which is around a third of what IBM takes. And bear in mind, we're still cheating here. These are triangles, not quadrilaterals. We're still not doing the blit operation. And I don't really see how IBM could even allocate an off-screen buffer without potentially interfering with what the programmer is doing elsewhere in video RAM. So it seems to me that the bottleneck must be in the hardware itself, specifically the fill routine of the card. But we've come this far already, let's push on and do the blit and see how long it takes. Or we could use the specialized ATI routine, which combines the fill and the blit into a single operation. Well, I seem to have run into a minor problem. I've set it up so it just draws triangles on the left-hand side of the screen now, and we'll fill them in over there, and then blit them over to the right-hand side so we can see what's going on. But let me show you what happens when I do that. As you can see, instead of copying the triangle image over, it's actually set all pixels of the destination blit rectangle the same color, namely the current foreground color, which is also what I was using for filling the triangles. So if I do a second triangle, you'll see exactly the same thing happens. Now, there is a mode of the blitter that's supposed to work like this. It fills all the destination pixels the same color, but that's not the mode that I'm using here. I'm using a special mode of the blitter, which is supposed to treat all of the black pixels of the original image as transparent, so when they get copied over, they don't affect the final image. And so in this way, we should be able to overlay triangles over one another on the right-hand side, which is the effect we're after. But as you can see, it's just not working. Now, I've been through my code with a fine-tooth comb, but the assembly code for doing the blitting just isn't that complicated. I've also been through the 400 pages of ATI documentation looking for some clue as to which option is interfering with the correct operation of the blitter. and unfortunately I just haven't been able to find it. I've also referred to a couple of other different documents on the 8514/A, and they just seem to broadly agree with what the ATI documentation says. So I'm really genuinely stuck. The thing is, we know that this card actually works because I certainly can't see any other way that the IBM adapter interface could overlay triangles on one another without using the Blitter. So the Blitter probably functions, it's just not described well enough in the documentation. Without some kind of example code, I'm not going to be able to make any progress with this. But one thing that I can do here is a timing. We are now doing the blitting step, and so we have the full code. It's just not displaying correctly. But the time should be correct. So let's do 10,000 of these. And unfortunately, it's still over 40 seconds, which is bad because we're actually now using half-size triangles since they're confined to the left-hand side of the screen. So I don't think that the problem with this card is actually the adapter interface at all. It's the hardware itself. It's great as a Windows accelerator where you just have rectangles that need to be filled. But if you wanted to use this for polygon fill in a 3D game, I don't think it'd be that great. You could use it for CAD/CAM work, but unfortunately the card is really much more limited than I originally thought.